When you start building games, you quickly realize that the same core systems get implemented again and again for every single project. Rendering, timing, animation, UI, asset loading, and so on. So instead of rebuilding these systems for every new project, what if we create a high-quality, reusable foundation? A solid base that we implement carefully once, and then use it to build many different kinds of games. We're building a reusable 2D game starter kit, completely from scratch, using plain vanilla JavaScript. No frameworks, no libraries. We'll focus on clean, data-driven design, production-ready practices, and a structure that allows our games to scale and grow while staying organized and maintainable. Let's build 2D games in JavaScript, and let's do it the right way. I create a div with an ID of game container that will help me with centering and scaling. And inside, I create a canvas element with an ID of game canvas. The HTML canvas is a programmable drawing surface in your browser that gives you control over every single pixel, making it the perfect tool for rendering interactive browser games. I link my CSS style sheet. I'm using Visual Studio Code, where the Explorer icon on the left sidebar displays your project files. To get started, I go to File, Open Folder, and I select my project directory. Once opened, you can manage your files directly in VS Code or through your computer's standard file explorer. I right-click the Explorer and create a new folder named CSS. Then right-click that folder to create a new file called style.css. Your project directory is now organized with index.html at the root and your style sheet inside the CSS folder. In style.css, first, I do a global reset to remove default browser margins and padding, ensuring our game canvas starts from a clean slate and behaves consistently across every browser. Now I have my code editor here and my web browser here on the right side. The body will have a background color, this midnight blue, and overflow hidden to hide any content that spills outside the screen. This will prevent scroll bars from appearing if your game canvas or objects move near the edges. Game container is the main wrapper here. If I want to see all my code, I go to View, Word Wrap to force long lines of code to wrap within the window, so you can see everything at once without having to scroll horizontally. Let's style game canvas first. I'll give it a border, 4 pixels, solid, this dark color is fine, and the background will be midnight blue. I set the body background to blue for now, and I refresh my browser window to see the changes. I set image rendering to pixelated to prevent the browser from blurring our graphics, ensuring every pixel stays sharp for that retro pixel art look. I also include crisp edges because different browsers use different names for this feature. Using both of these will ensure your game looks perfectly sharp across Chrome, Firefox, and Safari browsers. I set the font family to these fonts for now, and the font color will be white. Now I want to center the canvas within its parent game container, vertically and horizontally. To do that, I give game container display flex, height 100 viewport height, and position relative. I use justify content center to align the canvas horizontally, and align items center to center it vertically. In my project root, I create a new folder called JS to contain all the JavaScript files, keeping our logic separate from our styles and HTML. Inside that folder, I create a file called main.js, which will serve as the entry point for our codebase. In index.html, I create a script tag. I set type to module to enable modern JavaScript features like imports and exports, allowing us to split our game code into smaller, organized files that can share data with each other. I point the source attribute to the js/main.js file like this. Now we can go inside main.js and we'll start with a simple console log, just to see if our code is running. I'll say game starter kit loaded. Save that and refresh your browser. If you open the console using Ctrl-Shift-J shortcut in Chrome, you'll notice the code isn't running yet. Instead, you'll see a course policy error, cross-origin resource sharing. This happens because modern browsers block JavaScript modules from loading via a local path for security reasons. To make our code run, we need to host it on a local development server. The most common and the easiest way to handle this is through the VS Code Live Server extension. I'm using Visual Studio Code, but if you're using a different editor, feel free to use any local server you prefer. The goal is to simply serve our project via HTTP, so the browser allows our JavaScript modules to load. If you're in VS Code, just go to the Extensions panel and search for Live Server. Install the most popular version by Ritwik Day. Once installed, first completely close and reopen the code editor. Make sure your project folder is open by going to File, Open Folder. You should then see a Go Live button in the bottom right corner of your status bar. When I click it, it will start a local development server, and it should automatically open the project in a new browser window. The URL will be 127.0.0.1.5500 or localhost 5500. It also shows you the port down here, so you can even type the URL manually if it doesn't open automatically for you. Now if I open my browser console, I can finally see the console log message that says Game Starter Kit loaded. Our development environment is set up, and now we know how to create a local server the right way. By using a local server, instead of just double-clicking the HTML file, we're following professional web development standards. This setup allows us to build robust, scalable games that work exactly the same way in development as they will when we finally publish them online. Well done! Source code for the project at this stage is available to download in the resources section below. I called it Game Starter Kit Part 1. Use it if you hit a bug and want to compare your code to mine, or just save it as a checkpoint you can always come back to. I'll be providing source code checkpoints throughout this project to make sure everyone can follow along and nobody gets left behind. By the end, we'll all have a well-structured, optimized starter kit we can use to build many different games. Now that the project is set up, let's learn how to import and export JavaScript classes between modules, a key skill for keeping code organized and modular. We'll see how to break the game into separate files, share functionality between them, and make sure each module can communicate cleanly without creating messy dependencies. Inside my JS folder, I create a new subfolder I call Core. This folder will contain only the most important files that are crucial for our project to run. I right-click that new folder, choose New File, and I will call it Game.js. The Game.js file will be the central orchestrator that initializes all systems, manages the game loop, handles state transitions, and coordinates communication between all other components. It will be the brain of our codebase. For now, I will work with just these two files. Game will be a class because it fits the overall pattern better. I want some consistency across all the files to make sure the codebase is easier to navigate and understand. You can see I'm using the export keyword, which allows other files to import this game class using ES6 module syntax. This keeps the code organized and avoids global namespace pollution. Constructor is a special method that runs once when the class is instantiated, setting up all initial properties. Inside the class, we define properties using this dot. When I say this.canvas equals document getElementById gameCanvas, I'm storing a reference to the canvas DOM element in a property of this specific game instance. This way, all methods we add to the game class later can access that canvas reference. Basically, I'm saying create a reference on this particular instance of the game class, call that property canvas, and point it to the actual canvas HTML element. All the properties on a class start with this dot. To actually draw on the canvas, we need a drawing context, usually defined by the CTX shortcut. It will be equal to this.canvas.getContext2D. This allows us to use drawing methods like fill rectangle, draw image, and stroke to render graphics on the canvas. So this is my very simple basic game class. To actually use it, we have to instantiate it, which means creating a new object that uses this class as its blueprint. I go to main.js and import the game class from that file. If I look at my folder structure, main.js is here, and the game.js file we want to import is inside the JS core folders. So my import statement will be import game from ./core game.js. I start the path with // because it indicates a relative path from the current file's location, telling JavaScript to look in the current directory. I create a constant variable I call game, and it will hold an instance of this game class we are importing. To create an instance of a class, we use the new keyword, which will create one new blank object and run that class's constructor to give it properties based on that class's blueprint. If I console log game, I can see the class here, and it has canvas and CTX properties. Notice that because I'm using the live server extension, every time I save my project, usually I do that with Ctrl+S keyboard shortcut, it will reload the browser window and show me the updates. Game class will be the main brain of our code base. I give it a method I call resizeCanvas. Method is simply a function sitting on a class. There are a few ways people make browser games scale. The best way, in my opinion, is to have a stable internal resolution that never changes, and we just scale the entire canvas up and down to fill whatever available browser area we have. I will show you the right way to do this. Let's start simple and build it step by step. At first, we take this.canvas from line 3, access its width property, and set it to 150 pixels, just to test if these values actually work. I also set its height to 300. The game class will have an initialize method. I will call it init. Here we will run all the setup our game needs as soon as it loads. From here we will call this.resizeCanvas method we defined on line 9. When it comes to JavaScript classes, we have to understand that when an instance of a class is created using the new keyword, like you see here, it will run all the code inside the constructor once, as it's creating that new object. So if I want something to run at that point, I can simply call it from the constructor, like this.init. This will call the init method from line 8, which handles the initial setup of our game. For now, it only calls the resizeCanvas method from line 11. I got a reference error in my console, and it's because when I call resizeCanvas from inside its own class, I have to start with this dot, like this. Now, I can change the width and height values, and we can see it's all connected and working. Inside the JS core folder, I create another extremely important file called constants.js. This is basically our game data. For example, I can put all my weapon data, enemy data, specific win conditions for each game level, basically any static, never changing game data goes inside this file. If the game grows, we can split this file into enemy data, weapon data, and so on. We're all set up for that. But for now, we will keep all our data together inside constants.js. Notice I'm exporting all my constants and spelling them in capital letters, which is the most common practice. Our game will have a stable, never-changing internal resolution of 1280 x 720 pixels. In game.js, I will import game width and game height constants from constants.js, with the path defined like this. Here I'm defining and exporting constants in constants.js, and here I'm importing them into game.js. Now we can use them all around this file. So I will use game width here and game height here. Now we have a canvas that's 1280 x 720 pixels in size. It doesn't fit into my small browser window, so I want to add a very common resize logic pattern that will always keep this internal resolution but scale the entire canvas up or down. This ensures the full canvas, the entire game area, is always fully visible, regardless of the browser window size. First, we will need a helper variable for aspect ratio. 1280 x 720 is the standard 16:9 format. I will define helper-led variables for width and height. I can put each one on a separate line, like this, or I can define multiple variables in a single statement, like this. Same thing, just different syntax. I also want to have some margin, some space between the canvas and the edges of the browser window. I first have to calculate the available width we can work with. We don't have the entire browser window width. We have window inner width minus margin times 2, because the margin is on the left and right. Then we do the same for available height. It's window inner height minus the top and bottom margins. So available width and available height gives us the space we want to fit the canvas into, making sure it's always fully visible. Now I simply check the ratio of the current browser window's width and height. Based on whichever dimension is the limiting factor, I decide if I need to scale the canvas vertically or horizontally. If the ratio between available width and available height is more than 16:9, then we know that the window is too wide, landscape, so we're limited by height. We set h to available height and calculate w as height times ratio to maintain the 16:9 aspect ratio. Here I basically set the height to the actual height of the browser window minus the margins and adjust the width accordingly to keep the ratio. Else means that the window is too tall, portrait or square, so we are limited by width. We set width to available width and calculate height as width divided by ratio to maintain the 16:9 aspect ratio. Then I set canvas's internal resolution to game width and game height, which will always be 1280 x 720 in our case. But we scale the canvas up or down based on our formula by setting its styles: width, height and margin. I want to call this resize canvas method every time my browser window changes size. So here inside init, I add an event listener for the resize event. I use an arrow function for the callback because arrow functions preserve the this context, ensuring that this.resizeCanvas refers to the game instance rather than the window object. This is about JavaScript scope, which might be a bit more advanced for beginners, so don't worry about it too much if you're just starting out. Just keep in mind that this syntax is done on purpose. If you want to learn more about how this works, you can look up JavaScript arrow functions and this binding, or JavaScript context and scope. We now have what I think is a pretty elegant and clean resize formula, so let's test it. When I resize my browser window horizontally, you can see it ensures the canvas always fits the available width, while keeping the left and right margins of 5 pixels. If the limiting factor is the height of the browser window, it also scales down correctly, keeping the top and bottom margins. Our game always has a fixed internal resolution of 1280 x 720, but the canvas HTML element itself scales up and down. It will also work with any margin value you want. For example, I try 100, and if you don't want any margin, I simply set it to 0. I usually scale all my browser games this way. Do you like this technique, or do you have another preferred way to do this? Leave a comment and let me know. I'll leave the margin at 15 for now. This is the most critical method in our codebase, the game loop. It's an infinite cycle that runs roughly 60 times per second. Update game state, render graphics, repeat. This simple pattern is how every game, from Space Invaders to Baldur's Gate, creates motion and interactivity. I will define game loop as a method on my game class. We have our game class here, the main brain of our code base, and it already has an init method and resize canvas method, and now it has this new game loop method. The way we do this is by using the built-in request animation frame method, which tells the browser to call our game loop right before the next screen repaint, meaning right before the next frame gets drawn. I use this syntax because this arrow function preserves the this context of the class. By using an arrow function, this keyword still points to our game instance, so we can safely call this.gameLoop without losing access to our class methods and variables. If we didn't do it this way, this could end up referring to something else, like the window object, and our game loop would break. This goes back to the idea of JavaScript context, which is something many beginners struggle with at first. In simple terms, I want to make sure that this keyword always refers to our game class, while this line keeps getting called over and over again. The way I'm doing this is by using ES6 arrow function here, a modern JavaScript syntax that doesn't create its own this, but instead keeps the this value from where it was defined. So in this case, this correctly stays bound to our game class. Don't worry if you are a complete beginner and it doesn't make sense yet. For now, just remember that arrow functions bind this to the surrounding scope, so it keeps pointing to our game class instead of getting lost somewhere else. I'll add a console log here that says animating, just to check our game loop is actually being called over and over again. We're defining game loop here, but we still have to call it somewhere to actually start the process. We do that inside the init method. This line will trigger the first game loop call. It will run the console log, and then this line will schedule game loop again using request animation frame, which makes the whole process repeat continuously. Now if I open the browser console, I can see this console log being called over and over again, which means our game loop is working. One interesting thing about the built-in request animation frame method is that it automatically adjusts itself to the user's screen refresh rate. So if your monitor runs at 60 frames per second, the game loop will usually run about 60 times per second. On high refresh rate gaming monitors like 120 or 144, this will run more frequently, giving you smoother animations without having to change any code. This is one of the reasons request animation frame is the standard way to build game loops in the browser. Request animation frame also automatically provides a timestamp. To access it, I just assign a parameter here. I can call this whatever I want. The browser knows that the value passed into this function is always a timestamp. I'll call it t here and here. Now I console log timestamp, and I also add t up here, where we start the game loop. In the console, you can see that this timestamp is the number of milliseconds that have passed since the page started running. I can also divide this by 1000 if I want, and then I'll get a value in seconds instead of milliseconds. This timestamp comes from the browser's internal clock and is perfect for timing things like movement, animations, and later on calculating delta time. It's really important because it helps us make sure our game runs at the same speed on any device, whether it's a slow old computer or a brand new high-speed gaming PC. We'll handle that in a minute, but before we do, let's create a render method. I will use this.ctx from line 6. That's our canvas drawing context, which holds a set of properties and methods we can use to draw and animate shapes on the canvas. Back in render, first I set fill style to red. This.ctx fill style equal to red. I'll call this render method from inside my game loop here. Then I call this built-in fill rectangle method, and I pass it x, y, width, and height. This method takes the current fill style, in this case red, and draws a rectangle 50 pixels from the left edge, 50 pixels from the top edge, 200 pixels wide, and 200 pixels tall. Right now it's drawing the same shape over and over, but it looks static because nothing is moving, even though we already have a fully working animation loop. Let me prove it to you. Up here I define a this.x property and I set it to 0. Then I use it as the horizontal coordinate passed to fill rectangle, and every time render runs, I increase this.x by 2. Now you can see the shape moving to the right. It looks like it's getting longer, because we're not clearing the old drawings yet. Normally when you animate, you also clear the previous frame before drawing the next one to create an illusion of movement. We're not doing that yet, but you can clearly see that our game is already animating. Perfect. Clearing the canvas every frame is important, because otherwise the old drawings pile up, as you can see here. I delete this line, it was just a test. I also delete this line. And down here I set x and y to 0. And the width and height to game width and game height. I do this because I want the rectangle to cover the entire canvas, starting from the top left corner at coordinate 0, 0, and stretching all the way across the full canvas width and height. I can change the fill style to any color I want. I will go for this shade of navy blue. We can use this rectangle that covers the entire canvas as a simple way to clear the old drawings between each frame. By drawing a rectangle over the whole canvas every time, it essentially erases what was there before, so the animations don't leave trails. Source code for the project at this stage is available to download in the resources section below. I called it Game Starter Kit Part 2. Use it if you hit a bug and want to compare your code to mine, or just save it as a checkpoint you can always come back to. I'll be providing source code checkpoints throughout this project to make sure everyone can follow along and nobody gets left behind. By the end, we'll all have a well-structured, optimized starter kit we can use to build many different games. Now that we have a scalable canvas and a working game loop, let's create a render system to handle drawing all game objects to the HTML canvas in a clean and organized way. Time to create our very simple rendering pipeline. I right-click my JS folder, create a new folder nested under it, and call it Systems. In that new Systems folder, I create a new JavaScript file I call rendersystem.js. Its job will be to encapsulate all rendering logic, taking game data and translating it into visuals on the canvas, keeping our drawing code organized and separate from game logic. Inside, I will export class renderSystem. The constructor will take the canvas we are drawing on as a parameter and set it as a property on this class. Then I define a drawing context. This.ctx is equal to canvas getContext2D. We will draw everything from here. From game.js, I copy the entire render method and I paste it here. This code block will redraw the background, effectively clearing the canvas between every animation step, because that big background rectangle covers the old paint. We are using game width and game height constants here, so I have to make sure I import them up here. I go // because we need to go up one level from the systems folder back to the JS folder, then down into the core folder where constants.js is located. Back in game.js, I completely delete this render method and comment out this line where we call it. Up here, I import the render system class from rendersystem.js. To reach it, I use // to go one level up to JS folder and then systems rendersystem.js like this. The game class is the main brain of our code base. Here we initialize and instantiate everything and connect it all together. I create a new property called this.renderSystem, and it will be equal to new renderSystem. The constructor expects canvas as a parameter, so I pass it this.canvas from line 10. Doing this is called dependency injection, and we do it because renderSystem needs access to the canvas to draw on it. By passing it in rather than having renderSystem grab it directly, we keep our code modular, testable, and flexible. Dependency injection is a design pattern where an object does not create the tools it needs to work. Instead, those tools are injected, passed in from the outside. Now, to actually call that code, we want to call this render method from line 8. So I say this.renderSystem render. If I save that, I get a console error saying I can't find my constants file. And if I check, I am forgetting .js. Once I fix that, it works. So instead of putting all the drawing code directly inside our game class, which would quickly make this file huge and bloated, we'll organize all rendering logic in our render system file instead. This keeps our code modular, makes each system easier to understand, and allows our game class to stay lean and clean. I know we're not seeing much on the canvas yet, but right now we're laying down a strong foundation. One that's modular, easy to expand, and flexible enough to support many different types of games. From now on, whenever I want to draw something, our render system will handle it. Let's start with a very simple example. Let's say I want to use built-in canvas drawing methods to render a game grid. This will give our game a sense of scale and structure, making it easier to visualize distances and positions, and add some visual polish. The custom render grid method will first take this.ctx from line 6 and access its stroke style property, setting its value to yellow. I also set line width to 5 pixels. We will call this render grid method from inside render, which runs over and over again because it's been called from our game loop. Now I want to draw a simple line from point A to point B. To do that, I have to start with the built-in begin path method, which tells the canvas that we're starting a brand new drawing path. Then we use move2 to define the starting x and y position of the line. Next, I call line 2 to set the ending x and y coordinates. I can also chain multiple line 2 calls to draw several connected line segments and create shapes, but in this case, all we need is this simple line, so I call stroke to actually render it on canvas. Keep in mind that move to and line 2 only define a path. They don't actually draw anything yet. They just tell the canvas where the lines should go. To actually render the line on the canvas, we have to call stroke. I can move the starting x and y coordinates anywhere I want by changing the values I pass to move to. And I can also change where the line ends by passing different values to line 2. The line is simply drawn between these two sets of coordinates. We want to draw a grid, so let's start with the vertical lines. I will draw a line from coordinates 40, 0 to 40 game height. So it's 40 pixels from the left edge, and it stretches the entire game height, from top to bottom. This gives us a straight vertical line. I want these lines to cover the entire game area from left to right, so I create a for loop. It will run from horizontal position 0 all the way to game width, jumping by 40 pixels each time. Inside the loop, I use the current index, which increments by 40 as the horizontal position for both the start and end point of each line. Each line starts vertically at 0, the top, and ends at game height, the bottom. Perfect. You can see that this value determines how many lines we draw and how far apart they are from each other. Now, to create a grid, I have to do the same thing, but with horizontal lines. So I copy the previous code and tweak the values. The second for loop will run from 0 to game height in increments of 40. All these horizontal lines will start from the left edge, coordinate 0, and go all the way to the right, game width. Vertically, they will follow the index values, increasing by 40 as the for loop runs. Again, I can change this value to adjust the spacing of the lines. If we want a regular grid, these two values should always be the same. So I open constants.js and create a new constant called grid size. I'll set it to 40. Inside render system, I make sure to import it up here, like this. And then we use it here and here. And now we have a simple data-driven game grid. I can change the grid size value in our game data, and the render system will automatically handle all the drawing. From now on, whenever I want to draw something in our game, like a new enemy or a game object, I define its constants, non-changing properties inside our game data. Then I pass that data into render system, which takes care of rendering that game object on the canvas. I set stroke style to white here, and line width to 1 pixel. As you can see, my screen recording software might not capture all the lines correctly, but if you are coding along, you can see it's rendering fine. I need to make my canvas larger for my screen recorder to show the grid properly. I can also adjust the opacity here to make the lines semi-transparent. If you want to make a pixel art game, you can set image smoothing enabled to false, which prevents the browser from blurring your graphics when they are scaled. We now have a render system that handles all our drawing. Whatever you want to draw, we create a special method for it here. We call that method from render, which runs over and over again because it's been called from the main game loop. I delete this console log. Source code for the project at this stage is available to download in the resources section below. I called it Game Starter Kit Part 3. Use it if you hit a bug and want to compare your code to mine, or just save it as a checkpoint you can always come back to. I'll be providing source code checkpoints throughout this project to make sure everyone can follow along and nobody gets left behind. By the end, we'll all have a well-structured, optimized starter kit we can use to build many different games. Now that we've separated rendering into its own system, let's create a player entity and pass it to the render system so it can be drawn on the screen. Inside my JS folder, I create a folder called Entities. In here, I put all the game objects that have properties and behavior, like the player enemies, projectiles, power-ups, or anything else that exists and interacts in the game world. Let's create the player. Inside the JS entities folder, I create a player.js file. I export the player class, and inside its constructor, I define some properties. We'll need the x and y coordinates of the player, and we'll also need width and height. I'll set the player size to 64 × 64 pixels for now. I want to center the player in the middle of the game area, so I'll need to import game width and game height from the constants.js file. The player can later have all kinds of properties depending on what game we're building. For example, we might need some multipliers for permanent upgrades. For now, we'll keep the player very simple, just like this. We're exporting the player class, so here in game.js we import it, because as we know, this file is the main brain of our codebase that connects everything together. I give it a property called this.player, and it will be equal to new player. Now we have everything ready. I go to render system.js and create a method called renderPlayer. I set fill style to blue, and I'll draw a simple rectangle representing the player. For that, I'll need the x, y, width and height properties we defined earlier. We're importing the player class, instantiating it in game.js, and this renderPlayer method needs access to those values. I'll call renderPlayer inside the render method. First, we render the grid, and on top of it, in front of the grid, we draw the player. The order in which we call these render methods determines what gets drawn behind and what's in front. We know that renderPlayer will need access to the player object, so we can read player x, player y, player width and player height. We get that player object because it will be passed as a parameter to the render method. We already have this.player inside the game class, so I simply pass it as an argument to renderSystem.render, like this. This method expects player as a parameter, it passes it along to renderPlayer, and renderPlayer uses those values in fillRect to draw a rectangle at the player's position on the canvas. This might seem a bit complicated at first, passing the player around like this, but we do it on purpose. It keeps the system loosely coupled and maintains separation of concerns. The render system doesn't need to know how to create or manage the player, it only needs to know how to draw it. This makes our code modular, more testable and much easier to maintain as the project grows. Let's say I also want to highlight the player. I set stroke style to white and I call stroke rect at the player's x, y, width and height, like this. I set the background of the body to a dark color, something between midnight blue and charcoal. Inside renderPlayer, I also set the player rectangle to that same color. So here we have our player class. Sometimes you'll see a draw method directly inside the entity class itself, which takes x, y, width and height and draws the player right from here. We're not doing that because we want a proper, scalable and modular game architecture. Instead, we export the player class, we import it in game.js, instantiate it in the constructor, and we pass this.player to renderSystem.render. That method receives the player as a parameter, passes it into renderPlayer, and renderPlayer uses those values to draw the player on the canvas. I'm not adding a draw method directly to the player class because I want all rendering logic centralized in one place. This way, all canvas operations, draw order and visual effects live inside the render system, making it much easier later to add features like camera movement, screen shake, lighting or post-processing effects without having to modify every entity in the game. Source code for the project at this stage is available to download in the resources section below. I called it Game Starter Kit Part 4. Use it if you hit a bug and want to compare your code to mine, or just save it as a checkpoint you can always come back to. I'll be providing source code checkpoints throughout this project to make sure everyone can follow along and nobody gets left behind. By the end, we'll all have a well-structured, optimized starter kit we can use to build many different games. Now that we are drawing the player, let's learn a clean and easy way to add keyboard input so that we can control the player. The game class is the main control center of this codebase. It will have a property I call keys, which will keep track of which keys are currently pressed on the keyboard. At first, it will just be an empty object. I create a helper method I call setUpInput. We will call it here as part of the initialization sequence. Inside, we start by adding an event listener for key down event. Every time any key is pressed on the keyboard, this event will fire, and it will carry with it an auto-generated event object that holds all kinds of information about what just happened. Here I assign it to a variable called e. The e.key property holds the actual string value of the physical key that was pressed. So here I take this .keys property from line 11 and I use it like a lookup table, setting a property named after the pressed key to true. For example, if the W key is pressed, I set this .keys W to true. In my list of keys, I am marking the W entry as true. I use two lowercase to make sure all keys are stored in lowercase, which makes them easier to check later regardless of caps lock or shift. A lookup table is a data structure, usually an object or an array, used to store information so you can retrieve it quickly later without running complex logic or loops. In our case, we're using it to track the state of the keyboard in real time. Instead of treating a key press as a one-time message that disappears, we turn this .keys into a persistent status board. Whenever our game needs to know if the player is moving, it doesn't wait for a new event. It just checks which keys are currently marked as true. I'll run a console log here to verify the input system. If you log E, you'll see a massive amount of metadata the browser provides for every key press. When you log this .keys, you're seeing our live status board. Notice that keys are only added to this object once they've been pressed at least once. Every time we press a key, we add it as an entry to our keys object and set it to true. If the key already exists in the object, we simply update its value to true again. I copy this code block and I do something very similar for the key up event. Every time a key is released, we set its value to false. This is a simple, clean and powerful way to handle keyboard input. By tracking key states in a lookup table, we decouple input detection from game logic. The game simply checks the current state of the keys instead of waiting for individual events. This makes the codebase much easier to scale. It also gives us a native multi-key support, allowing combinations like holding W and Shift at the same time to sprint, which would be much harder to manage with a traditional switch statement. I'll adjust the line width and opacity of my game grid here. You don't have to do this. This is mostly because my screen recording software struggles with thin, transparent lines. I'm only doing this for this tutorial. Anyway, let's open player.js and make the player move. I give the player an update method. It will expect keys as an argument because the player object needs to check in with our keyboard status board to decide how to move. This update method will run over and over and will check if the W or arrow up key is currently true. If it is, we'll update the player's position in a certain way. For now, I'll just put this X++ here as a temporary placeholder. This game class will also have an update method that runs every frame. This is where all the logic in our game comes together. It will coordinate all the moving parts of our world on every single frame. We are importing the player class here, instantiating it, and saving it as a this.player property. This way, we can simply take this.player and call its update method here, like this. That update method is defined here, and we know it expects keys, so I pass it this.keys from line 11. Now I need to make sure I actually call this update logic from the game loop. I'll cut the game loop method and move it up here, just so I can see things next to each other. The game loop will run roughly 60 times per second. First, it updates everything, and then it renders everything. Right now, I'm getting a console log saying that a variable called W is not defined. That's because this is actually not a variable name, it's a string, so it needs to be in quotes. Perfect. Here, just for testing, I'm saying if W or arrow up is pressed, move the player in the positive direction along the horizontal x-axis. When I press W, the player moves to the right, so I can see my code is working. We should actually be moving in the negative direction along the vertical y-axis when we press W or arrow up. But anyway, this confirms the code works. Now we need to process these values a little bit before we pass them to the player and tell it where to move. I'll introduce two variables, dx and dy, which will help me calculate the intended direction of movement. I'll do something like dy minus equals 1 here. Let's do it properly. If dx or dy have a value other than 0, it means the player is trying to move. We then update the player's horizontal position x by dx and the vertical position y by dy. Keep in mind that since these values can be positive or negative, using plus equals automatically handles movement in all directions. Adding a negative number moves the player left or up, and a positive number moves it right or down. I'll give the player some speed. Let's set it to 10 for now. We account for that speed here and here. I'll explain exactly why in a minute, once we see the full picture. Here I say if the player is pressing S or arrow down, increase dy by 1. If the player is pressing A or arrow left, decrease dx by 1. And when D or arrow right is pressed, increase dx by 1. Notice that I'm using independent if statements rather than else if. This allows multiple blocks to run at the same time. I do this because it enables diagonal movement. By checking both horizontal and vertical inputs simultaneously, the player can move in two directions at once. I also give dx and dy a starting value of 0 every frame to reset them. So each frame, dx and dy start at 0. Input modifies them based on which keys are pressed. Movement is calculated and applied to the player's position. Then they are discarded and recreated on the next frame. This is called frame-based input sampling. We check the input state fresh every frame instead of storing movement values long term. Now, when I press WASD or the arrow keys, the player moves around. dx and dy are very small values between -1 and +1, so we multiply them by this dot speed to control how fast the player moves across the screen. Notice that when I move left, right, up or down, the player moves slower than when moving diagonally. Diagonal movement is faster, which is a very common issue in 2D games like this, so we need to normalize diagonal movement. We achieve that by calculating the vector length first, which is the square root of dx times dx plus dy times dy. This line calculates the length of the movement vector using the Pythagorean theorem. This is a very common formula you will see in any 2D game or animation project, because it's used for so many things. We have two sides of a right triangle, dx and dy, and the value we calculate is the hypotenuse, the longest side opposite to the right angle. Calculating this gives me the length of the movement vector. The movement vector is basically the direction the player wants to move in for this frame. Then I say dx/equals length and dy/equals length, which means I'm dividing both values by the vector length. This can also be written as dx equals dx divided by length and dy equals dy divided by length. Same thing, different syntax. I do this division because it normalizes the movement vector. It keeps the direction the same, but forces its length to be exactly 1. A vector is simply a value that has both direction and magnitude. In our case, the movement vector is made up of dx and dy, which together describe where the player wants to move. Normalizing a vector means keeping its direction the same, but changing its length to exactly 1. We do this so movement speed stays consistent. The player will not move faster diagonally than moving horizontally or vertically. Then I cut this code and I move it here. I delete this. So this is our movement formula. We reset dx and dy every frame. Then we check which keys are currently being pressed. If any directional keys are pressed during this frame, meaning the player wants to move, we make sure the player moves at the same speed in all directions by normalizing the movement vector. Then we actually apply that movement step in the direction the player wants to move by updating the player's X and Y positions. We will refine this in a minute, but first let's make sure the player can't leave the visible game area. We want to clamp this.x if it's less than 0 or more than game width. I start by using math.min, which chooses the smaller of two values. Game width minus this.width represents the farthest horizontal position the player can reach, without going past the right edge of the canvas. This is because on a HTML canvas, rectangles, like the one representing the player, are drawn starting from their top left corner, and they extend to the right and down. This.x is the player's current actual position. So I say, choose either the player's current position, this.x, or the maximum position at the right edge, game.width minus this.width, whichever is smaller. This.width is the width of the player. Whichever of these two values is smaller will be chosen. Doing this completely prevents the player from moving outside the canvas to the right. Then I wrap this line in math.max, which chooses the larger of two values, either the value we just calculated or 0. Doing this prevents the player from moving left outside the canvas, keeping the player's position at 0 or higher. So this single line ensures that the player can't leave the screen horizontally. If I test it, no matter how hard I try, the left and right edges of the canvas are now impossible for the player to move past. We do the same thing for the vertical Y position. Clamp the player between 0 at the top and game height minus player's height at the bottom, so it can't leave the game area in any direction. Our game might also include permanent upgrades or unlocks. One example could be a permanent player movement speed increase. We can handle that with a property I call this.speed multiplier, which I initially set to 1. We use it in these calculations here and here. If the multiplier is 1, the player moves at normal speed. I set the base speed to 5 here. If the multiplier increases to 2, the player will move at double speed. This is very useful if you have a game like Vampire Survivors, for example. You can increase the player's movement speed multiplier for every level up, or you can have it as a meta progression upgrade in a game shop. The only remaining problem with our movement formula is that it's completely dependent on frame rate. The player will move faster or slower depending on how many frames per second the game is running. We want all movement in our game to be frame rate independent. We want the player to move at the same speed, regardless of whether the game is running at 30 FPS, 60 FPS or 144 FPS. This will make the gameplay consistent on slow and fast machines, and this is how real games are made. We already learned about the timestamp that request animation frame automatically generates for us. If I console log it like this, you can see it shows the number of milliseconds that passed since the page started running. If I divide it by 1000, instead of milliseconds, we see the timestamp values in seconds. I'll comment this out and let's use these timestamps. We will need a helper property I call this.lastTime. Its job will be to hold the timestamp from the previous animation frame. Delta time is the amount of time that passed between the previous frame and the current frame. I calculate it by taking the timestamp from the current game loop and subtracting it from the timestamp from the previous cycle of the game loop. Delta time is basically the amount of time that passed between two animation frames. It tells us how much real-world time passed since the last frame, and by knowing this, we can time everything in our game based on real time. When I start the game loop, I set this.lastTime to performance now, which gives me the current high-precision timestamp in milliseconds. This value represents the exact moment the game loop starts, and we'll use it as a reference point so we can calculate delta time on the very first frame. We calculate delta time, and we can console log it to see its value. Each time we calculate delta time, we also set this.lastTime to the current timestamp, so that on the next frame we can correctly measure how much time passed since the previous one. If I run my code, you can see my delta time is around 16.6 milliseconds, which means about 16.6 milliseconds passed between the previous frame and the current one. That's because most screens, including mine, run at 60 frames per second, and when you divide 1000 milliseconds by 60, you get roughly 16.6 milliseconds per frame. I will remove this console log so we don't get console spam. I can also delete this console log. The update method will use delta time, so I pass it as an argument here. It will expect that delta time as a parameter here. I will move the update method down here just to keep myself organized. Update is now being called every frame from the game loop. It receives delta time for every frame as we are calculating it, and it will pass that delta time along to this.playerUpdate. Delta time will be the first argument, this.keys will be the second one. The order we pass these arguments in matters, because here we have to make sure they are expected as parameters in that same order. Now I can use delta time here when I update this.x and this.y to make the movement frame rate independent. By multiplying the speed by delta time, the time elapsed since the last frame in seconds, the player will move the same distance per second regardless of frame rate. This is because without delta time, faster computers would move the player faster, and slower computers would move the player slower. The game would run at different speeds on different devices. By multiplying by delta time, we're saying move this many pixels per second instead of move this many pixels per frame, which ensures consistent gameplay for everyone, regardless of their device's performance. A faster computer renders more frames per second, but it will have much smaller delta time, so the delta time value basically acts as a multiplier that balances out the frame rate. On a faster computer with many small frames, each frame moves the player a tiny bit. On a slower computer with fewer, larger frames, each frame moves the player a bigger amount, and both end up traveling the same total distance per second because of this. Keep in mind that delta time is the amount of time in seconds that has passed since the last frame, typically around 0.016 seconds for a game running at 60 FPS or 0.033 seconds at 30 FPS. Using delta time when calculating movement, animations, and time-based logic in a video game is one of the most fundamental techniques for creating smooth, consistent gameplay across devices. It's an industry standard practice that separates professional game development from amateur projects. Right now, my delta time is actually a value in milliseconds, but when I divide it by 1000 here, like this, I get a value in seconds. I do that because it's more intuitive to work with. When I set speed to 300, it means 300 pixels per second, which is much easier to understand and tune than 0.3 pixels per millisecond. Working in seconds is the industry standard and makes all our speed values more human readable. So this is how we make movement based on the actual time that's passing, making it frame rate independent. We pass delta time to update and use it in the movement calculations as a multiplier here and here. Keep in mind that delta time is the amount of time in seconds that has passed since the last frame. There could be situations where the browser tab loses focus, the user switches windows, or the game freezes momentarily, causing an abnormally large delta time spike. This is why I do this. I set delta time to the minimum value between the actual delta time value or 0.1. This caps delta time at a maximum of 0.1 seconds or 100 milliseconds. It prevents the game from making huge jumps when resuming after a pause, which could cause objects to teleport through the walls or create other physics glitches. I'm simply saying use the actual delta time or 0.1, whichever value is smaller, to make sure that in these special circumstances, delta time is never more than 0.1 seconds. No teleporting, no glitches, only smooth, time-based motion. With every feature like this we implement, we're building real game development skills. These are industry-standard, production-ready techniques used in professional games, from small indie titles to AAA releases. I hope you're getting some value. Let me know by leaving a comment if you want. Our current input system has a small bug. If you hold down a directional key to make the player move, and before you release that key, you right-click the canvas to open the context menu, and only then release the key up event never actually fires. As a result, the player gets stuck moving in that direction forever. The same thing can happen if you switch browser tabs or the window loses focus while the key is still held down. We can fix this very easily by clearing all keys when this happens. When the context menu opens, we listen for the context menu event and reset our keys to an empty object. We'll also clear all keys when the window loses focus by listening for the blur event. The blur event fires when the browser window or tab loses focus. For example, when you Alt-Tab to another application, switch tabs or click outside the browser. By resetting the input state in both of these cases, we make sure no keys get stuck, and our input system stays reliable no matter what the player does. You can test this by moving the player around and then right-click the canvas to open the context menu. As soon as the context menu appears, the player will immediately stop moving. I want to make sure the player's starting X and Y position is perfectly centered in the middle of the screen. I do that by setting the width and height first here, because we need these values to be available when we calculate this.x and this.y. Game width minus this.width divided by 2 will center the player horizontally. Game height minus this.height divided by 2 will center the player vertically. With this setup, we can change the player's width and height to any value, and it will always be centered. This calculation works because this.x and this.y represent the top left corner of the player, not its center. On a HTML canvas, rectangles and images are drawn starting from their top left corner and extend to the right and down. By subtracting the player's width from the canvas width and dividing by 2, we place the player so its horizontal center is in the middle of the canvas. Doing the same with the height aligns the vertical center as well, so the player is perfectly centered. For now, I'll set the width and height to 64 times 64. Let's take a look at our project structure. We are organizing our script files into separate folders on purpose, because our goal is for this project to be modular, easy to navigate, and scalable as it grows. I create a new folder directly nested under JS called Managers. This folder will hold files that manage and coordinate specific resources or systems, like loading and caching images, handling audio, managing game state, or controlling pools of reusable objects. Managers are responsible for organizing and providing access to shared resources that multiple parts of the game need. Inside, I create a file called ImageManager.js. Its job will be to load, cache, and provide access to all image assets in our game, acting as a central hub so we don't have to reload the same image multiple times or scatter image loading logic throughout the codebase. As usual, we export the ImageManager class and give it a constructor. Inside the constructor, we create a property called this.images, which will act as a container for all our loaded images. It will have a load method, a get method, and a load all method. Now we can see all the pieces we need for a simple image loader and manager. The load method loads a single image from a given path and stores it in the manager. We will use this whenever we want to add a new image to our game. The get method will return the image we ask for if the image finished loading. We will use this whenever we want to draw an image on the canvas. The load all method loads all the images our game needs at once. This will be useful at the start of the game, so we can make sure everything is ready before the game starts playing. The constructor creates this.images, which is an object that stores all the images along with a flag telling us whether they have finished loading. This helps us check if an image is ready before trying to draw it. The load method takes the name of the image and its path, loads the image, and stores it in this.images. First, we create a new image object and store it in a temporary variable called img. Then we set the src property, the source of that image, to the provided path. Next, we add an entry to this.images using the image name as the key. The value is an object containing the img we just created, and a loaded flag, which is initially set to false, and it will be updated to true once the image finishes loading. I take the empty image object we created, assign its source to the image path, and create an event handler for the image's load event. This handler will run when the image has finished loading successfully. When that happens, we find the image inside this.images using its name as the key, and set its loaded flag to true. I'll also run a console log for now, so we can see that our code is working. If I use backticks like this, it's called a template string, a modern JavaScript feature that lets you insert variables directly into a string using the $sign syntax like this. I'll simply log the name of the image that was successfully loaded. Then I add a simple error handler that will trigger when the image fails to load. For example, if the file path is wrong or the image is missing. I do this by assigning a function to ImageOnError. This function runs automatically if the browser can't load the image from the provided path. Inside it, I just log a message to the console so we know something went wrong and that the game will fall back to a placeholder instead of crashing. This way, our game stays robust. Even if the image is missing, everything keeps running. Adding error handling like this is something you almost always want to do when building a production-ready game. It helps prevent crashes and makes your game more robust. For a small hobby or prototype project, you can sometimes skip it, but it's still a good habit to get into early. The get method expects the name of the image we want as a parameter, and it returns that image to us. We can call it from anywhere in the codebase whenever we need to draw or use that image. If the image hasn't finished loading yet, the method returns null, which lets us safely fall back to a placeholder instead of breaking the game. If you've never seen this syntax before, this is called a ternary operator. It's a compact way to write a simple conditional. First, we have a condition to evaluate. Then, if true, do this, else do this. In our case, if the image we're trying to get has been loaded, we return that image, otherwise we return null. This loaded part is called optional chaining. It safely checks the loaded property only if the image entry actually exists. If the image name isn't found in this.images, optional chaining prevents a runtime error and simply returns undefined, which makes the condition safely fail and results in a null being returned. The job of loadAll method is to load every image our game needs at startup. This gives us a single place where we define all game assets, so they are loaded once and ready to use before we start rendering or updating the game. From here, we simply call the load method we defined on line 6 for every image asset in our game. We can see that load expects a name and a path as parameters. So inside loadAll, I pass it the name player. And for the path, I point it to an images folder that sits at the root of our project. Inside that folder, I will look for the player PNG image. In my project root, I create this images folder and I drag my player PNG image in. You can use your own image here, or you can download all project art assets, including the player PNG image I'm using from the resources section down below. I have this pixel art bug night just for now as a placeholder. This codebase will support all kinds of art assets. Even if you don't plan to make a pixel art game, all of this will still work. Okay, so our simple image manager is complete. Let's test it. We already know that game.js is the file where we connect everything together. So I start by importing the image manager class up here. I instantiate it here. And I call the loadAll method, which for now loads only one image, the player. This will call the load method, where we wrote logic that either uses the image if it's available, or safely fails and falls back. Fallback means instead of drawing the player image, we'll draw the blue rectangle representing the player. So after we instantiate image manager, we call loadAll like this. I get a console error that says cannot set properties of undefined. I see that error is coming from image manager.js on line 10, so I check it and I notice a small typo. This should be this.images. Now the code runs and in the console I can see image loaded player. Perfect. Now let's actually make our render system draw the image we are successfully loading. I make sure I instantiate this.imageManager and call loadAll first here, and then I pass this.imageManager into new render system as the second argument. I mentioned before that doing this is called dependency injection. Instead of the render system creating the tools it needs by itself, we create those tools elsewhere and inject them into it. In this case, render system depends on an image manager, but it doesn't know how to create one. It just expects to receive one. That keeps our system loosely coupled and easier to test, reuse and maintain. If render system created its own image manager internally, the two systems would be tightly coupled. By injecting the dependency through the constructor, we stay in control of when and how that dependency is created. This is specifically constructor injection, which is one of the most common and clean ways to do dependency injection in JavaScript. I open RenderSystem.js and make sure Image Manager is expected here as the second parameter in the constructor. Then I store it as a class property called this.ImageManager. From this point on, we create a live connection between RenderSystem and Image Manager. RenderSystem doesn't load images by itself. Instead, whenever it needs an image, it simply asks Image Manager for it. Because Image Manager was injected from the outside, RenderSystem stays focused purely on rendering. It doesn't care where the images come from and how they were loaded. It only cares about drawing them on canvas. This keeps our architecture clean, modular, and easy to extend later. For example, if we want to add more images, swap image loaders, or add loading screens without touching the rendering code. We know that Image Manager has a get method that expects the name of the image we want, and it checks whether it's loaded and returns it to us. Notice that we're calling the image we want player here, spelled exactly like this. So here, where I render the player, I create a helper variable called playerImage. It will be equal to Image Manager get player, the name of the image we want. We know that Image Manager will either give us the image or return null. So here I say, if playerImage is not null, if we actually manage to get the playerImage, then draw it. On the canvas, we use the built-in drawImage method, which needs at least 3 arguments: the image we want to draw and the x and y coordinates where to draw it. These x and y coordinates define the position of the top left corner of the image, and the image extends to the right and down from that point. This means images and rectangles are rendered in the same way on the canvas, which makes this very easy for us. We can also give drawImage optional 4th and 5th arguments for width and height, which allows us to scale or stretch the image. In this case, I simply pass player width and player height. So if we successfully get the player image, we draw it, otherwise we draw the placeholder rectangle representing the player. The actual image I'm using for the player is 64 × 64 pixels, but I can resize it if I need to. For example, doubling it to 128 × 128 will cause the drawImage method to scale the player accordingly. Because we're drawing the image using the same x and y values as the player's rectangle, it stays positioned consistently in the game world. Right now, the player is moving at 100 pixels per second. I can easily make the movement faster, for example 300 pixels per second, by adjusting this value. For testing, I'll completely delete the player image from the images folder. As you can see, the fallback rectangle is drawn instead. In the console, I'll see the custom message we prepared that says something like image failed for player, will use fallback. If I put the image back into the folder, the game renders it again as expected. At this point, we have a system for handling images in our game, and if an image fails to load for any reason, the game will still run using placeholder graphics instead of crashing. Source code for the project at this stage is available to download in the resources section below. I called it Game Starter Kit Part 6. Use it if you hit a bug and want to compare your code to mine, or just save it as a checkpoint you can always come back to. I'll be providing source code checkpoints throughout this project to make sure everyone can follow along and nobody gets left behind. By the end, we'll all have a well-structured, optimized starter kit we can use to build many different games. Now that we are drawing the player as a simple sprite and we are able to move it around the game world using keyboard input, let's add some UI. There are 2 main ways web games handle drawing UI: directly on the HTML canvas or using HTML elements, which is substantially less code and allows for easy advanced animations using the built-in power of CSS. I set this.lastTime to 0 because it gives us a safe initial value before the game loop starts. I adjust the line width and stroke style opacity of the game grid. Feel free to use any values you want here. I set the player to 64 × 64 pixels and use 0.2 alpha for the grid lines. We now have a player moving around the canvas, and we've created a solid, scalable foundation for so many systems. We can turn this into many different types of games. I put begin path and stroke outside the for loops because I want to draw the entire grid in a single path instead of many separate ones. Inside the loops, I only define the line segments using move_to and line_to. By calling beginPath once before the loops, all those lines become part of the same path. Then, when I call stroke once at the end, the canvas draws all grid lines in one go. This is more efficient than starting and stroking a new path for every single line, and it also keeps the code cleaner and easier to read. The resulting game grid will look exactly the same. Now it's just optimized. Let's create a main menu for our game. Inside index.html, I will create it down here inside game container, after the canvas. I create a div with an ID of main menu. I give it a class UI panel. This will be a shared class that allows me to style all UI panels in our game together. I also give it a second class called active. When this class is present, the UI panel will be visible. When we remove this class, the UI panel will hide. I give my game some temporary title here, and under the title I create a HTML button element with an ID of play btn, play button. The text will say play. After the button we can add some text, whatever you want to tell your players before the game starts. For example, I can tell them to press WASD to move and escape to pause the game, which we will implement soon. You can see that my new main menu is squished next to the canvas, so let's open Styles CSS and make it look good. I'm going to handle all my UI panels here. UI panel will be a shared class. Every element with this class will get position absolute, which removes it from the normal document flow, and it's no longer affected by the layout of the canvas or the other elements. This lets us freely position UI panels on top of the game canvas. Because the parent container, game container, is set to position relative, the UI panels will be positioned relative to the game container instead of the entire page. This makes it much easier to center menus and keep everything aligned with the game. I give all UI panels a black, slightly transparent background. I use the backdrop filter property and set it to blur 10 pixels. This blurs whatever is rendered behind the UI panel, not the panel itself. The result is a frosted glass effect, where the game is still visible in the background, but softened, which helps the menu stand out while keeping a sense of depth. The border will be 3 pixels solid, and I use a neon sky blue color, because I'm going for a glowing neon effect. I add 30 pixels padding, and border radius 15 pixels. I set text align center, and box shadow 0, 0, 30 pixels, using the same sky blue color with reduced alpha to create a misty, translucent glow around the panels. I set z-index to 1000 to make sure UI panels are always on top and in front of everything else. We will show and hide the panels by manipulating their display property. If display is set to none, the panel hides. But here you can see we gave it an additional class called active. If the active class is present, a UI panel with that class will be set to display block. So now we just need to remember that to show or hide any UI panel in our game, we can simply add or remove the active class. We can do that very easily with JavaScript. The game title will use the same sky blue color, margin bottom 20 pixels, and font size 40 pixels for now. I also add text shadow using a similar color with some transparency. Here I will style the buttons. All of these can be just base styles, and we can do another pass later to match the styling better to the final art style we decide to use in our game. The background will be this deeper denim blue color, and the text color will be white. The border will be 2 pixels solid neon sky blue. The padding is 12 pixels top and bottom, and 14 pixels left-right. Margin will be 8 pixels. I increase the horizontal padding to 24 pixels to make the button wider. Font size is 16 pixels. I set cursor to pointer, which makes the cursor turn into a hand when hovering over the button to indicate the button is interactive. The font family will be this for now, just as a placeholder. We can use a more custom font later. I set border radius to 8 pixels, and to animate the button on hover, I set transition all 0.3 seconds. The box shadow again uses the transparent blue we've been using. Let's give the buttons a hover animation. I will simply change the background color and give it a glow. using box shadow, like this. As a final touch, I use transform translate -2 pixels to move the button 2 pixels up on hover. What do you think about our main menu? I think this looks pretty decent for a start-in design. We can also add images, animations or other buttons. For example, a shop button for permanent meta upgrades could go here, if the game you are designing includes it. Inside the game class, after the setup input method, I add another method called setup UI. I will also have methods hide all panels and start game. If the game grows larger, we can move this into a dedicated UI manager class inside the managers folder. But for now, for a game this size, this is good. We have the play button we created here. I gave it an ID of play btn. So inside setup UI, I get that button element by ID and assign an onClick event handler. When we click it, it will run this.startGame. Notice I'm using an arrow function here to bind the context, to make sure this.startGame keeps pointing to the startGame method on this class, even when the click event fires later. The hide all panels method hides all UI panels at once. Any UI element we create with the UI panel class will be affected. So for example, the main menu panel or the pause panel. I do this by using document query selector all to select all elements with the UI panel class. This returns a list of elements, and I iterate over that list using for each. For each panel we find, I access its class list property and remove the active class. If you remember, we set up our CSS so that UI panels are only visible when the active class is present. By removing that class, the panel is hidden. UI panels have display set to none by default, and only adding the active class sets display to block, making them visible. So by removing the active class from all panels, we hide them. Inside start game, I call hide all panels, because once the game actually starts, we don't want any UI panels covering the canvas anymore. By centralizing this logic inside hide all panels, we avoid manually hiding individual panels in multiple places, which keeps the code cleaner and easier to maintain as the UI grows. We also need to call the setup UI method up here inside init, where we do our entire initial setup. So now we've added an event listener to the play button. When I click it, the start game method should run, and the first thing start game will do is to call hide all panels, which includes the main menu panel. When I click play, the main menu should disappear. It doesn't disappear, so I check my console, and I'm getting a reference error inside game.js on line 62 saying class list is not defined. It happened because inside for each, I'm trying to iterate over all UI panels. I assign each panel a temporary variable called p, which represents each panel during this loop. So if I want to access CSS classes on the panel we're currently iterating over, I need to access class list on p, so p.classList, and then remove the active class, like this. When I fix that, the error goes away, and when I click play button, UI panels are properly hidden and the main menu disappears. Right now, we have no way of showing the main menu again, so I reload my browser window and click play again. Yes, it works. Notice that right now, when the main menu is visible, you can still move the player around underneath it. That's not something we want, because the game should be paused while we're in the menu. To prevent that, let's add a simple state management system to control when the game is allowed to update and respond to input. We'll keep track of whether the game is in the playing state, and only then we will run our gameplay logic. So when the start game method runs, we set this.state to playing. I define this.state up here, and initially I set it to menu. Our game will start with the main menu open. Inside the update method, which runs repeatedly, we check if this.state is not equal to playing. If we are not playing, we return, which prevents the rest of the update method from running. For now, this method only moves the player. If we are not playing, the player won't update or move. I test it, I'm pressing WASD and arrow keys, but the player is no longer moving under the menu. Only when I click play, we move the player around. Perfect. I reload the page, movement is not possible. I press play, and I can move. Nice. On the main game class, up here, between update and setup input, I create a method called render. If the game state is menu, we draw a dark navy rectangle covering the entire canvas. This creates a simple menu screen. We can also add other visuals here, depending on how we want the menu to look. Otherwise, only when the state is not menu, we call render system render, which will draw all game objects. I call this render method from inside game loop after calling update. So inside render, we check the game state. We either draw the main menu background or render the entire game. When I'm in the main menu, the game grid is hidden and we only see the dark navy rectangle covering the entire canvas. When I press play, our render system starts drawing all game elements. For now, that includes the game grid and the player. When we are in the menu state, we draw the menu background on the canvas. Otherwise, when we are in any other game state, such as playing or paused, we draw the game world. Source code for the project at this stage is available to download in the resources section below. I called it Game Starter Kit Part 7. Use it if you hit a bug and want to compare your code to mine, or just save it as a checkpoint you can always come back to. I'll be providing source code checkpoints throughout this project to make sure everyone can follow along and nobody gets left behind. By the end, we'll all have a well-structured, optimized starter kit we can use to build many different games. I will fix the spelling here to image failed. Inside index.html, down here after the closing div tag for the main menu, I will create a pause panel now. A div with an ID of pause menu and the shared UI panel class. Inside a h2 title that says paused in capital letters, I will give it a secondary class I call active, which we know will make the panel visible because of the CSS we wrote earlier. Inside, I create a button with an ID of resume btn, and the text will say resume. One more button with an ID of quit button, which will say quit to menu. You can see the buttons already have styles and hover animations because we wrote this CSS earlier when we made the play button. If I remove this active class, the pause panel will be hidden. On this div inside the main menu panel, I do some inline styles where I set margin top to 20 pixels and font size to 12 pixels. I can do inline styles here because this is just a small one-off visual adjustment that only applies to this element. If I needed to reuse these styles, I would move them to the main CSS file instead. So we know that by adding or removing this active class here, we can show and hide any UI panel in our game. In styles CSS, I copy this block, and for h2, I set the font size to 35 pixels. The pause panel will be hidden at first. I open game.js, and down here, I create a new helper method I call pause. Another I call resume, and one more method I call quit to menu. I will also create a helper return to menu method because we might need it for future proofing. I will get back to this later. When the pause method runs, we set this.state to paused. In the resume method, we set this.state to playing. Inside return to menu, we set this.state to menu. And from quit to menu, for now, I simply call return to menu. When we pause the game, we want to show the pause menu panel. We use document.getElementById to get pause menu, and then we use class list add active to give it that additional active class and make it visible. Inside resume, I do the same thing, but remove the active class to hide the pause panel. Hide all panels will hide both the main menu panel and pause panel because it targets all elements with the UI panel class, which we included here and here. So when we return to the main menu, we call hide all panels, including the pause panel and whatever other panels we might add in the future. And then we show the main menu panel by finding it, using its ID, and adding the active class again. Okay, I can press play to hide the main menu. Now we need a way to show the pause panel while we are playing. Inside the key down event listener, I will set up the escape key to toggle pause on and off. If the key we pressed is escape and the current state is playing, we call pause. Else, if the state is paused, we call resume. I can press play, press escape to pause, and the pause panel appears. Now I want to be able to click the resume button to continue playing. So down here inside Setup UI, I find resume button using its ID. I add an onClick handler, and when the resume button is clicked, the resume method runs. When quit button is clicked, we run the quit to menu method. I can press play, escape to pause, resume button to resume gameplay, escape to pause again, and quit to menu button. And we are back inside the main menu. Notice that when I play again, the player stayed at whatever position it was standing before. We want to reset some things like this whenever we start or restart the game. Whenever the start game method runs, we want to reset the player position. I set player X to game width divided by 2 and player Y to game height divided by 2. I will also set this.last time to performance now, because we need to reset the time reference. Otherwise, if the player was in the menu for a while, the next frame's delta time calculation could be huge, potentially causing the player to teleport or objects to jump when the game resumes. Performance now gives us the current high-resolution timestamp, so the next frame starts measuring from this exact moment. This way, delta time on the first frame after starting or resuming the game is small and predictable, instead of including the time spent sitting in the menu. Even if we have other precautions to prevent these glitches, it's still a good practice to include it here. I open main.js and I will remove these two console logs. Inside ImageManager.js, I comment this console log out. I want a clean console like this for now. I can close this. I play the game and I press escape to show the pause panel. I set the alpha of the background on all UI panels to 0.2, making them more transparent so that we can really see the backdrop filter blur in action. The way this works is, if I make my window larger, it creates this frosted glass effect. Game elements like the player are still visible when they are behind the UI panels, but they are blurred like this. It's just a small detail, not that important, but I think it looks nice. We have a small bug here. Notice that initially I'm using this formula to center the player rectangle exactly in the middle of the screen. But if I look inside game.js, here when we call start game, we are resetting the player's position, but not accounting for its width and height. So this will not center it exactly in the middle. We want this formula, which will correctly center both rectangles and images representing the player. A much cleaner approach here is to give the player a reset method, where we reset the position, but we can also reset other things in here, like this. What we reset here will depend on how we design our game. For now, this is good. Here, inside start game, I delete these lines, and I will call this.player.reset instead. I play, I quit, I play again, just to make sure the player is resetting correctly. It works. Just to keep it simple, I have this quit to menu method, and all it does is to call this other return to menu method. I will simplify this for now. I completely delete this, and from here, when quit button is clicked, I will call return to menu directly. I play, and I quit to menu, just to check if everything still works. Perfect. We can do a little bit of defensive programming here, especially because next we will handle proper asset loading with promises. we want to prevent the first delta time from being 0 or undefined. Maybe here I can say if this.lastTime is 0, set this.lastTime to the current timestamp. We are setting this.lastTime to performance now here, just before the first loop starts. I will get back to this when we implement proper asset loading for images and audio. I might review this again if it's actually necessary. It's not actually that important at this point. Source code for the project at this stage is available to download in the resources section below. I called it Game Starter Kit Part 8. Use it if you hit a bug and want to compare your code to mine, or just save it as a checkpoint you can always come back to. I'll be providing source code checkpoints throughout this project to make sure everyone can follow along and nobody gets left behind. By the end, we'll all have a well-structured, optimized starter kit we can use to build many different games. Inside index.html, we have main menu and pause panel. And down here, I will create a loading screen. A div with an ID of loading screen. It will have a shared UI panel class and active class to show and hide it. Same as we do with the other UI panels. Inside, I give it a heading that says loading and maybe some text. You can put anything you want here. We could even have a set of phrases that appear randomly. I might do that later. Okay, so here we have a very simple loading panel. We will handle the loading here inside the init method. But before we do that, we have to adjust our image manager a little bit. I will add promises. Inside the load method, I will return a new promise, which will wrap our image loading logic. Notice it has this resolve parameter, which is a callback function that we call when the promise completes. I will put all the image loading code inside this promise. I put the resolve function at the end of onLoad and also at the end of onError. Doing this means that the promise will complete successfully whether the image loads correctly or fails, allowing our game to continue either way. We resolve on error instead of rejecting because we have a fallback rendering system that can handle missing images, so a failed image load shouldn't stop the entire game from loading. This allows load_all to use promise_all to wait for all images to finish loading in parallel before the game starts. In JavaScript, a promise is a special object that acts as a placeholder for a result that hasn't happened yet. Because some tasks, like fetching data from a server or loading an image, take time, JavaScript uses promises to manage that waiting period without freezing your entire program. Notice I'm using async await here in load_all. Async await is a syntactic sugar over promises that makes asynchronous code easier to read. I do it because I need to wait for all images to finish loading before the game continues. The await keyword pauses execution until promise_all finishes, and marking the function as async allows me to use await inside it and makes load_all return a promise that my game class can also await. We will add more image assets here later. This load now returns a promise that resolves when the image loads and also if the image fails to load. The load_all method is asynchronous now, and it will wait for all the promises we put inside to resolve, which in this case means it will wait for all the image assets we put here to load. Back in game.js, I use the async keyword here before init, and inside I say await promise_all. And I cut this.imageManager load_all like this from the constructor, and I paste it inside promise_all like this. Notice we have async await here. I'm basically saying, wait for all these asset managers to finish loading before continuing. Promise_all takes an array of promises and waits for all of them to complete in parallel. Once everything is loaded, init will continue and it will hide the loading screen and show the main menu. Using promises here will make sure the game never starts with missing assets. We know that we can show and hide UI panels by adding or removing the additional active class. So when the game loads and we enter the main menu, I want to hide the loading screen and I want to show the main menu UI panel. Initially, the main menu will not have the active class. Only loading screen will have the active class at first. If I reload my page, we might see a brief loading screen flicker, but we have only one small image asset for the player, so the loading is almost instant. Just for testing, I will make the promise take a little bit longer to resolve so we can see a proper loading screen for a second or two, and we can really visually verify that all our code is working. Inside load all, I add a new promise that will simply have a set timeout, which will resolve after 2 seconds. Set timeout is actually spelled like this. Set timeout is a built-in JavaScript function that schedules a specific piece of code to run only after a designated period of time. In this case, I'm saying create a new promise that will wait for 2 seconds and then it will resolve. And we know that load all will wait for all the awaits it has before it can continue. So this artificial delay will keep the loading screen visible long enough for us to verify it's working properly. Of course, we'll remove this delay later once we've confirmed everything works. We know that the init method here is asynchronous and it will pause at this await line until image manager load all resolves, which now includes that 2-second delay. Only then it will continue to the next line and hide the loading screen and show the main menu. And the game only becomes interactive once everything is ready. Perfect. I reload my page one more time. That works, nice. In style CSS, I give the loading screen some extra padding. Save that, reload the page, loading, and we are in the main menu. Awesome. This is a clean and simple way to add a loading screen to your game. Of course, we can make the loading screen more interesting later with images or animations. We have the base infrastructure here to handle all of that. Source code for the project at this stage is available to download in the resources section below. I called it Game Starter Kit Part 9. Use it if you hit a bug and want to compare your code to mine, or just save it as a checkpoint you can always come back to. I'll be providing source code checkpoints throughout this project to make sure everyone can follow along and nobody gets left behind. By the end, we'll all have a well-structured, optimized starter kit we can use to build many different games. We now have a solid foundation that can save you a huge amount of time when building 2D games in JavaScript. If you feel there's an important system missing, something every game should have, let me know. I may expand this with additional lessons in the future. Now it's time to take what we've built and use it to create complete games. Experiment with it, adapt it, and push it further. If you'd like more structured, step-by-step guidance on building full games from start to finish, you can find related classes on my instructor profile, where we apply these foundations in complete projects. Well done on finishing the class. Hope you found some value.